Yes, welcome to the course on high performance computing. I am Professor Vijay Dange. Today we are discussing about the first unit of this course, that is introduction. So before starting with this unit, before we are discussing about what is the objective of this course. So first of all, the first objective is to study parallel computing hardware and programming models. Then to be conversant with performance analysis and modeling of parallel programs. Then to understand the options available to parallelize the program, and to know the operating system requirements to qualify in handling the parallelization. To study programming aiming at scientific computation, then to study tools for performance optimization and debugging, and other ways for performance improvement. So these are the objective of this course. Then next point is about course outcome. So after studying this subject, you should able to know something about this subject. So student is able to describe different parallel architecture, interconnect networks, programming models, then develop an efficient parallel program algorithm to solve given problem. Then student will be able to analyze and measure performance of modern parallel computing systems. Then student will be able to build the logic to parallelize the programming task. Then student will be able to solve problems for multi-core or distributed concurrent parallel environments, and student will be able to write the application using parallel programming approaches. So these are the outcome of this subject or the course which student will get after completing this particular course. So let's discuss about the contents, what we are going to discuss as part of this particular unit. So first of all, we are discussing about motivating parallelism, why we have to go for parallelization, then scope of parallel computing, then parallel programming platforms, implicit parallelism we are discussing, then what are the trends in microprocessor and architectures, then limitation of memory system performance, then dichotomy of parallel computing platforms, physical organization of parallel platforms, communication cost in parallel machines, scalable design principles, architectures, and wide superscale architectures and multi-core architectures. So these are the different points which we are going to discuss as part of this particular unit number one, step by step. So let's first start with the introduction. So what is HPC? So as we know that the high performance computing, as name suggests, it's a high performance computing denotes a certain way of using computational devices so as to maximize their performance, performing as much calculation per unit time as possible. So ultimately we are using available computational devices to maximize the performance of particular system by executing a number of operations per unit time. So if we are to maximize something, we need a way to measure it. So the basic measurement unit of performance in HPC is called flops, that is floating point operation per second. So this is the unit which is used to measure the performance of any parallel computing systems, or we can say supercomputers, which are available. So modern computers are capable of performing millions of billions flops, that is floating point operations per second. So derived units are usually used instead. So nowadays, to measure the performance of any parallel computing system or high performance computing system, is measured that how many floating point operations are executed per second by that particular system. Based on that, the performance of that parallel system is measured. Then let's see about what is HPC in terms of different units which are derived from the basic unit, that is flops. So first of all, one mega flops, it is known as one flops, which is equal to 106 floating point operation per second. Then 1 gigaflops, that is 109 flops. Then 1 teraflop, that is 1 T-flop, is 1012 flops. Then 1 petaflop is equal to 1015 flops, and 1 hexaflops is equal to 1018 flops. So these are the different units which are derived from basic flops. Then most microprocessors today can do up to 4 floating point operation per second per clock cycle. Means in one clock cycle, 4 floating point operations are executed by particular microprocessors which are available today. So at least this is theoretically, but a very simplistic way to calculate the maximum performance of computing device is to multiply the number of cores by the clock frequency by 4. So this is the way how we can calculate the performance of particular device. Then there are some examples are shown here. Typical theoretical performance of various computing devices is mentioned, like smartphones which are available with us, that is, and similar gadgets. Around 1 to 2 G flops operations are executed per second. Then laptops and desktops can execute around having the speed, or we can say performance is up to 10 G flops. Then high-end servers which are used for different applications are having around 25 to 100 G flops. And then graphical accelerators having around 20 G flops, or 20 G flops to 2 T flops. Then one rack of IBM Blue Gene computing systems is having around 14 T flops, and TI2 around 54 P flops. There is around 54,000 G flops operations are executed per second. Then next point is about where is the HPC's use, or where the role of HPC is. So first of all, the HPC is used by both science and industry. So it is used in different areas in science and industry. In scientific studies, HPC is used to create digital experiments, models of physical systems whose behavior is being examined through governing equations, calculations. Example include weather prediction. Suppose if we want to do some calculations, and to perform this computation is very complex. So to get the solution of that particular one within small time span, we need to use a high performance computing system. Then discovery of new medicines, then nanotechnology, and discovery of new materials, disaster prevention, etc. So in different areas, basically this HPC is used. Then major industries which are using HPC are oil and gas companies, pharmaceutical companies, defense and aerospace organizations, automobile manufacturers, financial institutions, and many more. So basically, as we are going to study this HPC, while studying this, we should know about some laws, that is Moore's law. We need to going to discuss as part of this, because it is going to be the motivation for the parallelism. So obviously HPC is quite useful and has a lot of applications, but it needs high performance computing devices in order for it to work. So ultimately, as we are discussing, that HPC is having wide scope or applications in different areas, but as at the same time, we need to have the high computing devices to work them combined as a parallel computing system. So it is obvious that computing device gets more powerful each day, but what is the rate of this increase, and is there a limit? So nowadays, as we see that there is a development, as we see the evolution of computers, basically at early age the computers are of vacuum tubes or a number of transistors and all, and nowadays you can see that all these things are get replaced by a small chips. Okay, so that is basically nothing but the evolution, and that will result into increasing the power of computation as well. So Moore's law is the observation that over the history of computing hardware, the number of transistors on integrated circuit doubles approximately every 2 years. Means the number of transistors which are going to be used for in design of integrated circuits are get doubled approximately every 2 years. This is nothing but the law which is stated by Moore. Then combined with other factors that help to increase performance, this means that the computing power is doubling each 18 months. Okay, Moore's law is the reason you always regret that you brought your laptop the minute you walk out of the store. They always begin selling better models on the next day. As we are going to see that whatever configurations we have, okay, yesterday, today maybe that configurations are going to be upgraded. So that is the nothing but there is a change or the integration of the different operations or the different functionalities are going to be integrated as part of this. So Jordan E. Moore, one of the Intel co-founder, described his tendency in 1965 and predicted it will continue for at least 10 more years, and it has preserved with frightening accuracy of almost 50 years now. So the next point which we are going to discuss as part of this is a motivating parallelism. So the first motivation for parallelism is the computational power argument. So from transistors to flops. As we have seen that the actually the computing systems, initially they are having transistors, and nowadays you can see that the computational power of transistor is increased as part of different floating point operations, and that is nothing but the basic motivation for as part of parallelism. So computational power argument from transistors to flops is the one of the motivation. So in 1965, Jordan Moore made the following simple observation: the complexity for minimum component cost has increased at a rate of roughly a factor of 2 per year. Certainly, over the short term, this rate can be expected to continue, if not to increase. Over the longer term, the rate of increase is a bit more uncertain, although there is no reason to believe it will not remain nearly constant for at least 10 years. That means by 1975, the number of components per integrated circuit for minimum cost will be 65,000. Then second argument or second motivation for parallelism is memory disk speed argument. As we know that the speed of the overall speed of computation is determined not just by speed of processor, but also by the ability of memory system to feed into it. So feed data into it. So while clock rate of high-end processors have increased at roughly 40 per year over the past decade, so DRAM access times have only improved at the rate of roughly 10% per year over this interval. So from this statement, you can easily get the idea that the processing capability is roughly increasing 40% per year over last 10 decades, but the memory access time, okay, is not going to be increased with that much speed. So parallel platforms typically yield better memory system performance because they provide large aggregate caches. So by providing aggregate caches at different levels, the performance of parallel system can be achieved. Then higher aggregate bandwidth to the memory system. So whatever the time taken for transferring data from memory to your processor is also get increased. That is also the reason to get to improve the performance of memory system in high end systems. Then last argument is data communication argument. So in this particular one, as the networking infrastructure evolves, the vision of using internet as one large heterogeneous parallel distributed computing environment has begun to take shape. So as nowadays you can see that everything is available online, and that is the reason why we should not use this different computational power, okay, by means of using data communication, as different devices all over the world are interconnected by means of internet. So is it possible to use the computational power of different devices even if they are located far away from each other? So many applications lend themselves naturally to such computing paradigms. So some of the most impressive applications of massively parallel computing have been in the context of wide area distributed platforms. So in many applications, there are constraints on the location of data and or resources across the internet. So an example of such an application is mining of large commercial data sets distributed over relatively low bandwidth networks. So in some applications, data is distributed at different locations, or resources are not available at one location. So by using the data communication argument, we can combine or we can use these different resources for getting the particular application to be executed on that particular one, so that the computational capability of different devices, which are, even if it is presented is available at different location, can be used to um, resolve or to solve the problem. So these are the different points what we have discussed in this one. So summary, in summary, we are discussing what we have discussed, that we recap. So we have discussed about course objectives, which we can what we can study in this subject. Then what is the outcome, means once we complete that course, then what student is able to do. Then we have discussed about introduction to high performance computing. We have discussed about what is SPC, then what is the floating point operations per second, that is unit which is used for performance measurement and all. Then example performance also we have discussed. We have discussed about different uses of HPC, that is in science and industry. Then we have discussed about Moore's law, which is also useful as it states that after every 18 months the number of transistors are getting doubled, okay, on an integrated circuits. And lastly, we have discussed about the motivation for parallelism. So what is the motivation for parallelism? As there are three motivations what we have discussed, that is computational power argument from transistor to flops, then the memory or disk argument, and lastly we have discussed about the data communication argument. So these are the three different motivations for parallelism. Then these are the references which we have used for this particular topic. Okay, thank you.